Below are two parallel charged conducting plates. The plates are separated by a distance of 2 meters. And between the plates we have two positively charged objects. The one on the left has 1 coulomb of charge, and the one on the right is 2 coulombs of charge. The electric field strength between the plates is a uniform 10 newtons per coulomb. And we're going to move each charge from the negative plate to the positive plate, neglecting any effects of gravity. We'll also assume that the particles don't exert forces on each other. First, I'll draw the electric field lines. Next, I want to calculate the electric force that's exerted on these particles. So these particles are going to be attracted to the negative plate, and they will each feel a downward directed force, which is an electric force. Let's calculate each of those electric forces. We'll do it for the 1 coulomb charge and the 2 coulomb charge. For the 1 coulomb charge, it will be 10 newtons. And for the 2 coulomb charge, the electric force is 20 newtons. Next, we'd like to calculate the work the electric force does when the particles are moved from negative plate to positive plate. Let's say that a person is going to physically grab the charges and move them from negative plate to positive plate. In order to do that, they have to supply an upward force, a force of push. And it has to be a greater force on the 2 coulomb charge in order to achieve constant velocity than they have to apply to the 1 coulomb charge. They're going to have to push with 10 newtons on the 1 coulomb charge and 20 newtons on the 2 coulomb charge. I bring this up because I want to see how much work a person would do in moving the charge from one plate to another. For the 1 coulomb charge, it would be 10 newtons times 2 meters, positive 20 joules. For the 2 coulomb charge, it requires 20 newtons of force times 2 meters. So that's going to require 40 joules of work. Now let's see what work the electric field will do in this case. So we need a displacement of 2 meters. That will be our delta y. For both particles. And we see that the electric force is directed opposite of the displacement. So there's 180 degrees between them. This means the electric force will actually do negative work. And the formula we can use for this will be negative Q times E times delta Y. So, negative 1 Coulomb times 10 newtons per Coulomb times a delta Y of 2 meters gives us negative 20 joules. We know it's negative because the displacement is opposite of the electric force. For our other particle, the calculation will be negative 2 coulombs, 10 newtons per Coulomb, 2 meters, negative 40 joules. Next, we'll calculate the change in each object's electric potential energy, which is called delta U sub E, as a result of being moved from the negative plate to the positive plate. It can be helpful in these situations to look at the scenario and decide where you think the object will have more potential energy. Electric potential energy can be thought of as an electric field's ability to do work on a particle. If the positive particle is already on the negative plate, then the field doesn't have as much opportunity to do work as it would when the positive particle is near the positive plate. If the positive particle is near the positive plate, then the field has a lot of ability to accelerate that particle because it doesn't want to be there, and it can push it all the way to the negative plate. So it's just helpful to know that our positive particle will have more electric potential energy at the top than it will at the bottom. And we'll actually call the bottom here 0 electric potential energy. Now, electric potential energy in a uniform field has a formula. The formula is U sub E equals Q times V sub E. And we can replace V sub E with another expression, E times Y. And at this point, we can create a coordinate system where up is the positive Y direction, and we can let the negative plate be a Y of 0. But we want to examine our equation and the situation to make sure that it makes sense. When Y is 0, our electric potential energy should be 0. When Y is a positive value, then we want a larger electric potential energy, which we would have. So this looks good. Let's calculate the initial. It will be 1 Coulomb, 10 newtons per Coulomb times 0 is 0. And then let's calculate the final. One Coulomb, 10 newtons per Coulomb, 2 meters. Our final electric potential energy is 20 joules. That's how much work it takes to move the particle from negative plate to positive plate, and it's also how much potential energy it will gain when it's there. This was for particle 1. We can also do the calculations for particle 2. For particle 2, we will have a UEI of 0 when it's on the negative plate. And when it's raised in the air, it's going to have 40 joules of electric potential energy. So, to answer the question, the delta UE for particle 1 will be 20 joules, and the delta UE for particle 2 is 40 joules. The reason why it's more is because the charge has a larger Q. And lastly, we'll use electric potential, V sub E. It's similar to electric potential energy, but it's potential energy per unit charge. Calculate delta VE for each particle's move from the negative to positive plate. What factors actually determine the size of delta VE? And we also want to draw equipotential lines inside our capacitor. Alright, so a formula for delta V will be delta U over Q. And we'll do this for the first charge. The delta U was 20 joules, and it was a 1 coulomb charge. Therefore, our delta V for the first charge is 20 joules per coulomb. We'll do the same calculation for the second charge. And again, we get 20 joules per coulomb. What this shows us is that the potential of the particle depends only on its position in the field. So I'm going to draw a equipotential, and this equipotential will be the V equals 0 potential. At the top, we have the 20 joule per coulomb equipotential. And we can make as many equipotentials as we wish. This one would be the 10 joule per coulomb. It's just telling us how much work it takes to move a coulomb of charge to this new location. It takes 10 joules to move a coulomb halfway to the positive plate, and it'll take 20 joules in all to move a coulomb from negative to positive plate. If we want, we can make more of these equipotentials. This would be a 5 joule per coulomb equipotential, and this one could be a 15 joule per coulomb equipotential. The unit joules per coulomb is so important in electricity and magnetism that it's been given its own unit. And the unit is called a volt.